Welcome to Project Phoenix, a capstone design project by Jonathan Heffley, Jose Hein, and myself, Daniel Perlin. This project focuses on the development of an additively manufactured Aerospike nozzle. Traditionally, rocket motors use what is commonly referred to as a bell nozzle, shown on the right. However, this nozzle is limited by its expansion ratio, which determines at what altitudes it can effectively fire. This CFD simulation for the bell nozzle on the right shows the Mach contour, in which the exhaust is overexpanded, leading to instability and efficiency loss from flow detachment along the nozzle walls. On the right, however, we have an Aerospike nozzle, which we also design along with this particular bell nozzle geometry. From these images, it is clear how the Aerospike avoids the inefficiency and instability issues a bell nozzle can experience under varying ambient atmospheric conditions. One of the major disadvantages limiting the adoption of the Aerospike over traditional bell nozzles is the complexity of the design part. Our aim is to mitigate some of the challenges by creating an Aerospike from two 3D printed pieces, which we compare with the bell nozzle as a control measure. This 3D printing process also opens up the door to vastly oversimplifying the cooling system, which would be required on a full-scale Aerospike rocket motor. Our motors are also designed to fit onto the fairly common Cicerone Pro 75 motor hardware used for sounding rockets, which paves the way for conducting physical tests and launches. This motor was designed with future testing in mind. The propellant to be used for hot firing the motor consists of 3D printed ABS plastic fuel grain combusting with gaseous oxygen. A pressure transducer is also installed into the motor inlet to measure chamber pressure. Finally, in partnership with the College of Engineering's Ares laboratory, a test stand was developed to be able to safely conduct cold flow and hot fire tests of the motor. A finite element analysis simulation was conducted to verify the factor of safety on the forces experienced by the thrust frame, which is shown in the middle and at the bottom left. As an added safety measure, due to the highly experimental nature of this project, the test stand was also designed with blast shielding protection in order to protect against any potential motor failure conditions.